Welcome to Calculus. Today, we will investigate finding one-sided infinite limits, focusing on one-sided behavior of rational and trigonometric functions around their asymptotes. Let's take a look at two examples, one of each. Our first example is a rational function. So our first task is to graph this function by creating a table of coordinate points. Then I want to find the indicated limit. In this case, the limit as x approaches -1/2 from the left-handed side of this x over 2x plus 1. And then I want to write the equations of any vertical asymptotes. Let's graph the function to begin. So I'm going to create a table of values. Remember, when we're graphing rational functions, though, before we make that table of values, it's really useful to come up with the horizontal and the vertical asymptotes. So just to recap, how do we find horizontal asymptote for a rational function? Recall that that's a comparison between the highest power on x in the numerator with the highest power on x in the denominator. So I'm going to investigate there. I see that the highest power of x in numerator is 1. Highest power on x in the denominator is also 1. So recall, if they're equal, the high powers are the same above and below. We find the equation for the horizontal asymptote by using the coefficients on those two x terms. So the high powers equal in numerator and denominator. And so I'm going to find these two coefficients on those x terms. So my horizontal asymptote is going to be of the form y equals, and I don't have a given coefficient on the x in the numerator, so I'm going to supply a 1. So I've got the equation y equals 1 over, and then the coefficient on my high-powered x in the denominator is 2. So I'm going to graph that. That is a horizontal line going through the y-axis at 1/2. Let's also find the vertical asymptote. So we found the horizontal asymptote by comparing the high powers above and below. Turned out they were the same, so we took the coefficients. For the vertical asymptotes, remember, we find those by setting the denominator of the rational function equal to 0, and then we solve. So I'm going to rewrite that denominator. It's 2x plus 1. I'll set it equal to 0, and then I want to solve that. And really what we're claiming with the vertical asymptote is that's a discontinuity in the graph. So 2x equals -1, divide both sides by 2. And here's our equation for our vertical asymptote. Is x equals -1/2. And just like we sketched in the horizontal asymptote, I'm going to sketch in the vertical asymptote through -1/2 on the x-axis. Now I do want to notice we kind of were clued in that that was our vertical asymptote by the value of the limit. Notice we are investigating what's happening in the graph around that vertical asymptote at x equals -1/2. And we're focusing on the left-hand side. So notice this superscript of minus means from the left hand. So I've got my framework in place. I want to create the table of values. And really what I need to see is, where do points fall to the left of that vertical asymptote? Where do points fall to the right? So I'm not going to choose a lot of values. I want -2. fact, I think I can go with probably just two values. -2 would be on the left hand of the vertical asymptote, and then I could go with, let's go with +1 on the right side. So I'm going to calculate, and really I just need to see where do they fall, and then I can place the two branches of the rational function. So f at -2, I'm going to replace x values with -2, so that's -2 over 2 times -2 plus 1. So that's, to simplify this fraction, -2, 2 times -2 in denominator is -4, plus 1 is -3. So that's +2/3. So I'm going to go ahead and plot that point. That's -2, +2/3. So the horizontal asymptote's at half, so this is above it. So what I can assume is that this graph, that left-hand branch is above the horizontal asymptote. Let's do the same for the y value at +1. That one's on the right side of the vertical asymptote. So again, just substituting in 1 for any x, so it's 1 over 2 times 1 plus 1. And that's going to reduce to 1 over 2 times 1 is 2, plus 1 is 3. So that's 1/3. So at 1, 1/3 is less than the horizontal asymptote at half. So this right-hand branch is going to be mostly down below. In fact, all below that, it just kind of skates up into quadrant 1 as it approaches the horizontal asymptote. Well, we've graphed it, and in fact, we found the equation for the vertical asymptote as part of our graphing. All we need to do now is determine the value of this limit. So when I look at the function, and I'm considering that I'm approaching x from the left-hand side, it's really this left-hand branch. As it gets close to -1/2, we just need to ask ourselves, where is that left-hand side heading in terms of its y value? And you can see it's shooting like a rocket towards the heavens. That's infinity. So we would finalize that by saying the limit as x approaches -1/2 from the left-hand side equals infinity. And that I can box. Let's take a look at a second example that's a trigonometric function. So our instructions are the same. I want to graph the trig function with a table of values, and I want to write the equation of any vertical asymptotes, and then I want to determine the value of the limit. In this case, as x approaches -3 pi over 4, also from the left-hand side. In this case of the trig function, negative secant of 2x. So with the trigonometric function, I want to set that table up at the outset. And I'm going to leave some room to do the work there. So I'm going to put x here. And what I'm noticing is that 3 pi over 4 is pretty much in the center of that graph. I'm sorry, -3 pi over 4. So I'm going to calculate values around it. So I'm going to back up to -pi, include -3 pi over 4. I'll put in -pi over 2. So I'm tracking to the right towards the y-axis. So -pi over 4. And then let's also calculate at 0. And what we'll see, this is an infinitely repeating function. So if we can catch the pattern, then we can make the iterations from the one piece. So we're looking at negative secant of 2x. And so what I would like to do at this particular function is calculate its y values using the unit circle. So we need to remember the definition of secant. Secant of x is the inverse of cosine of x. So when I'm thinking in terms of unit circle, cosine is x over r. So if it's the inverse or the reciprocal, it's going to be the radius over the x value. Let's put a unit circle here so we can visualize it. And that'll get us started. So let's use this definition of secant in our chart with the unit circle to come up with these function values, the y values. So our first substitution is negative pi for x. So it's negative secant of 2 times negative pi. So then I'm going to simplify that angle measure. So it's negative secant of negative 2 pi. So I need to locate negative 2 pi on the unit circle. So remember, from the 0 starting place on the unit circle, the positive direction is counterclockwise. So the negative direction is clockwise. So that's what we'll be focusing on. We're going we're going clockwise with this example, since all the values we're looking at are negative. So for us, negative 2 pi, remember 2 pi is a full revolution around the unit circle. That's back here at 0. So really what we got to record is what is the value of cosine there at that starting point at 0 or negative 2 pi. So cosine there would be 1 over 1. So this is also going to be 1 over 1, because you flip 1 over 1, you still have 1 over 1. Now there is a negative sign out front here on the function. So that's negative 1 over 1, which reduces to negative 1. So I'm going to plot that here. I've got a value here at negative pi of negative 1. Now let's calculate with negative 3 pi over 4. So secant of negative secant, sorry, of 2 times 3 pi over 4. Let's reduce that interior part. Again, that's negative. Equals negative secant of the angle. Now, if I multiply 2 times negative 3 pi over 4, that's negative 3 pi over 2. So if I think in terms of my unit circle, I'm really backing up to this, what we would call usually pi over 2 or 90 degrees. But since I'm going negative direction, that's negative 3 pi over 2. So the value of cosine there is 0 over 1. The x component of that triangle on the y-axis is 0. The radius is 1. But when I invert that, because remember secant is the inverse of cosine, it's 1 over 0. In fact, negative 1 over 0. But that doesn't matter. That's undefined. The sign on there doesn't change. In fact, we're trying to divide by 0. So let's again think in terms of what does undefined look like on the graph? That's a vertical asymptote. So right there at negative 3 pi over 4, there's a vertical asymptote. Let's see what happens when we calculate negative pi over 2. So that's negative secant of 2 times negative pi over 2. Just like in the previous two calculations, I want to simplify this angle. So 2 times negative pi over 2 is simply negative pi. And if I place that on my unit circle, that's over here on the negative x-axis. So again, the value of cosine at negative pi is negative 1 over positive 1. The inverse, again, secants, the reciprocal of that, that's 1 over negative 1, which is negative 1. But I did forget I had a spare negative out front here of secant, so it's negative 1. The double negative resolves as a positive. So at negative pi over 2, I'm at positive 1. So if we can calculate a couple more values, we can see the pattern in the secant graph, and then we can just make the rest of the graph based on that pattern. So let's calculate these last two. Negative secant of 2 times negative pi over 4 is negative secant of 2 times negative pi over 4 is negative pi over 2. And that's really going in even increments kind of back around the unit circle. So this is negative pi over 2. And that, again, the cosine value at negative pi over 2 is 0 over 1 again, because again, this is a vertical place. Cosine is the x component. There is no x component at the y-axis. So that's 0 over 1, but secant's the inverse, so it's flipped over. And this is, again, negative 1 over 0, which is undefined. And just like our last undefined function value, what that appears on the graph as is a vertical asymptote. So what I can see is that I've got a vertical asymptote at regular intervals. They're centered at pi over 4. And it looks like they are pi over 2 wide. So I'm going to recreate regularly spaced vertical asymptotes, at least to fill our coordinate plane. We understand that they go infinitely to the left, infinitely to the right. We'll just fill them up on our plane so that we get the sense of that. The last value, and you can maybe predict this. What do you think it is based on the pattern? Negative pi was negative 1. Negative pi over 2 is positive 1. So 0, what would you predict? We'll calculate. So negative secant of 2 times 0 is negative secant of 0. So we're back at the beginning. So again, that's right here on unit circle. So cosine of 0 is 1 over 1. The inverse of 1 over 1, which is secant, is 1 over 1. We had a spare negative out front, so that's negative 1 over 1, which is negative 1. And I think that was your prediction. So I see this alternating pattern in between, exactly in between vertical asymptotes. It's either negative 1 or 1. So I can fill in the others, the remaining ones on my coordinate plane, so that they're alternating. And then recall secant's graph are U-shapes that reach a minimum or a maximum at these points that we've graphed between the asymptotes. So starting here on the left, the way I would graph this is an upward bound U, an downward opening U, an up opening U, down opening U, and so forth. So that's our graph. Took a second to get it, but we found it there in the end. We could even catch that left-hand piece there. All right, so what we need to do at this point is find the value of the limit at this particular x value. So just to investigate again, we were looking at negative 3 pi over 4, and we're approaching from the left-hand side. So I'm going to find negative 3 pi over 4. I'll just highlight it in the green here. So it is a vertical asymptote. The left-hand side's down below the x-axis. So where we're looking is what's the tendency of the y value of the negative secant of 2x on the left-hand side of negative 3 pi over 4. That's headed down infinitely. So what we would say is that's headed to negative infinity, and we can make the claim that the limit as x approaches negative 3 pi over 4 from the left of this negative secant of 2x is negative infinity. Let's box that. The last thing for us to do is to record the equations of any asymptote. So you'll notice here we've got an infinite number of asymptotes. So we got to write the equations for them in such a way that we can catch them all. So I'm going to start with this positive one at positive pi over 4. I know we were focusing at negative 3 pi over 4, but notice they're at pi over 4 intervals, and I'm adding pi over 2 to pi over 4 to get each one. So the way I could do that is say that this is pi over 4, and remember vertical asymptote is x equals. But then what I'm doing is I'm changing the coefficient on pi for each one, because like let's just write a few of these. It's negative pi over 4, negative 3 pi over 4, negative 5 pi over 4. So I see that what I'm doing in my numerator is I'm adding a 2 to the coefficient of 1 every time. So the way I would write this is that it's parentheses 1 plus 2k times pi over 4, and k is some integer. All right. And if I switch out and use all the integers, I would catch all of those different vertical asymptotes separating the u shapes of the secant function. Thank you for joining for this investigation of finding one-sided infinite limits of a rational function and a trigonometric function. I'll let you go work on some of your own one-sided infinite limit questions. Thanks for joining. See you soon.